Then we're going to break it into the parts. We're going to use those undetermined coefficients. And remember what the rule is? The numerator is 1 degree less than the factor in the denominator. It's not the degree of the denominator, it's the degree of the factor in the denominator. Okay? We're going to get rid of the fractions. We're going to clear those out of there. And then we're going to solve that for the undetermined coefficients using either convenient zeros or some other numbers that we might want to plug in, a system of equations, or we can use that Oliver Heaviside cover-up method. Now, did the cover-up method work on very many of them? No. Only non-repeating linear factors. Did I recommend you do that? No. Maybe on 1 or 2 of the problems, and the rest of them, what is your mainstay technique? Convenient zeros, and when we run out of convenient zeros, then you're going to use system of equations. Okay? All right. So don't forget the last part. Rewrite the original problem in terms of the 2 undetermined coefficients that you found. So just a quick reminder, here's what we did on this one. We factored it. Degree of the denominator for each one of these was 1, so the numerator's degree 0. So just a plain old A and B, just those 2 separate parts. Okay? Found out what A and B were. We said this is okay, I don't have a problem with this, but this would look a little bit better. If you look it up in the back of the book, if you've got a fraction for A and B, it probably would look nice to write it that way. We did this problem right here, which was interesting, hopefully, because this demonstrates the idea of why we have to write down a repeated linear factor. We have to write it with a power of 1, and we have to write it with a power of 2. We're basically saving a place for that if it was there. Remember the starter question yesterday? Yeah. Like we didn't save a place for it?
Yeah. If we just kept going and got the 2, the A and the C, and the B, would we still get and cancel back out? If we get
No, you wouldn't. Okay, so let's say, so Tylen's question is this. We didn't save a place for it. We didn't get that. We figured out A was this, and we figured out C was that. And then we just combined this with this, put them together. The question is, will it equal the original problem, which is what the whole goal of partial fraction decomposition is. The answer to that is no. If you put the 2 of those together, you will not get this right here, which is why it's so important that you save a place for every one of those possibilities. Okay? Any questions? Yeah.
So would good fail-safe be like once you're done with it, try to put it together?
If you had time. If you had time. But these, I mean, we're taking a half a page of paper for each one of these. It takes a while to do these. Okay? All right. Any questions? Okay. Yeah.
How many of these about will we have?
16.
16?
You're going to have 3. One will be easy, one will be medium, and one will be hard. Okay? And tomorrow you'll have a quiz with a medium to a difficult one on it. So you make sure you get, if you can do the homework tonight on 8.5, the quiz tomorrow ought to be a breeze. Okay? Because once you get in the groove of these, they're not hard. You start them out the same way every single time, and you go through that process. Factor it, break it up into its parts, plug in the convenient zeros. Once you run out of those, if you don't have all the undetermined coefficients figured out, you start plugging in numbers or you use that system of equations, okay? So let's do this one right here. This is number 14. It may or may not be on your assignment, but it's out of the book. It's just like the stuff that you're going to see. What favor have they done for us? It's already factored. So would you please break that up into some parts? One part for each one of the factors in the denominator and its repeats. So one part for the x plus 2, one part for the x minus 1. Degree of the factor in the denominator is 1, so this is going to be degree 0, so that's just going to be an A, and this is just going to be a B. Next step, okay, again notice, we're saying this side equals this side over here. We don't like working with fractions, so we're going to get rid of the fractions. And when we do that, we just multiply by the denominators, because that's going to cancel off all the denominators. And again, this works this way every single time. This side is just 3x. It's just what the numerator was. This one's always going to be a times the other factors. This one's just going to be b times the other factor. Any questions there? Okay, so what?
Would it matter if we had a over x minus 1?
It wouldn't matter. If you wrote the x minus 1 first and the x plus 2 first, you're still going to end up with the same number over the x minus 1 as if you wrote it in the other order. Okay? Right. The whole things are going to switch, the entire terms. Good question. Anything else? Okay. How many undetermined coefficients do we have? 2. How many convenient zeros do I have? 2. This is going to be easy. We're going to get both of them using the convenient zeros method. So I'm going to take x equals, what am I going to plug in first? Yeah, probably a 1. Let's plug in a 1. If I do that, I get a 3. Am I going to write this? No. I'm going to plug in a 1 and I get 3b. So that tells me b equals 1. I'm in good shape there. What is the other convenient zero? Negative 2. So I plug that in, I get negative 6. I am going to write this because this is going to be negative 3a. Am I right? Am I going to write this? Not even going to bother. Okay? So that means a is equal to 2. So I've got both of these. Again, you wouldn't want to stop there. That's a common mistake. People just kind of relax, say, oh, I know what a and b are, so I'm finished. The whole point of this is to write this as the sum of the parts of the fraction that it came from. So this is going to be 2 over x plus 2, and this is going to be 1 over x minus 1. That right there is the answer. Any questions? So back to Tylen's question. What if we wrote the x minus 1 first and the x minus 2 second? So what if it were this? We'd have a over x minus 1 plus b over x plus 2. We would have figured out that a would have been 1 and b would have been 2. Okay? See how they just correspond? They go with each other? Nope, doesn't matter. You can write them in any order you want. Just don't look at your neighbor's paper and say, hey, you got a equals 5 and I got a equals negative 3. Somebody did something wrong. Check and make sure what order you wrote them in, because if you wrote them in different orders, you're going to get the answers in different orders. Any questions there? Okay. Could that one be done using the cover-up method? Yes, it could. Okay. Might be, I mean, you could quickly double check this. If I cover up the x plus 2, what am I plugging in? A negative 2. That would be negative 6 on the top and negative 3 on the bottom, so that means a would be 2. Okay? Parker. Do you want me to do it? Sure, you can. Watch. Okay? So the system of equations one would be, we're going to take this, and I'm basically going to compare the polynomial on this side to the polynomial on the other side. So this is 3x. Now, if I needed to, I don't need to on this one, but I could say, hey, I don't have any x squareds and I don't have a plain old number. One of those is going to be important. Then I'd go through and I'd say this is ax minus a plus bx plus 2b. With me there? I just distributed through. I'm taking this and I'm distributing through. Okay, and then I said, please do yourself a favor and write it down the way I told you to. This side, we're going to collect the x's together. So start a set of parentheses. That's got an x on it, so there's an a. That's got an x on it, so I write plus b, close the set of parentheses because I've got those taken care of, slap an x on the end. Start a set of parentheses, and it's always better to put pluses. If you wanted to put a negative out front, you could, but you're just asking for a nightmare of keeping things straight. So I'm going to write a plus, and then I've got a minus a and then plus 2b. With me there? Now, on the other side, do I have any x squareds over here? No, so I don't need to write that. What I do need to write is 3x plus 0. And then I go through and I'm going to color code this. So there's a 3 in front of the x. There's an a plus b in front of the x. So a plus b had better equal 3. If I color code this one, 0 had better equal negative a plus 2b. So now I've got a system of equations. I know that 3 should equal a plus b, and I know that 0 should equal minus a plus 2b. Now, that's a lot of work. You can ignore everything from there back and just say, I need to solve this system of equations. I'm going to solve it by elimination. Gosh, if you wanted to make a matrix out of this and solve it using matrix equations, you could. Okay? But look, this is a 3. The a's go away, and this is 3b. So what's b? B is equal to 1, just like we found before. So see how that's just nice confirmation there? Is that enough? Okay. Anything else? Okay, let's take a look at the next one. This is the first one we've run into like this. Okay, what favor have they done us? It's already factored. What is not so nice about the factors? Okay, it's got an x squared and that does not break down. That's what we call an irreducible quadratic. It is not a linear factor. Linear factors are very easy to work with. Quadratic factors are a little bit more difficult. Okay, so here's what we're going to do. It starts out the same way. I'm going to write down a part for each one of the factors and its repeats in the denominator. You can. Okay. What's the degree of the factor in the denominator? Degree 1. So that means the numerator is degree 0, so it's a plain old number. What degree is the factor in the denominator here? Degree 2. That means the numerator would be degree 1. Degree 1 means it's got an x in it. So here's what we write. We write bx plus c. Hold on. Okay. If it's degree 0, you know it's just a plain old number. If it's degree 1, you know it's got an x in it. Could it have a plain old number also? Despite how much Tylin doesn't want it to have a plain number, it could have a plain number. So this falls in the same category of we're going to save a place for every possibility. If it turns out that there is no plain old number there, what will C be? It will be 0. Okay? All right. Now, the great part about this is, take a good look. We're going to do the same thing that we've always done. I'm going to take this. It's an equation. It's got fractions in it. I don't want the fractions. So we're going to multiply by x plus 1, x squared plus 4. Distribute through. Look what happens here. That's a 1, just like it always is. It's just the denominator, or the numerator sticks around. This is going to be a times x squared plus 4. This is going to be bx plus c. That's the entire top. Yes, you should put it in parentheses. And it's going to be multiplied with x plus 1. Okay, now, this is the first one we come across where this is a fair amount more difficult. Okay, so do we have any convenient zeros?
Yes.
I do have a convenient 0. So I'm going to take that convenient 0 and I'm going to plug it in. So I'm going to plug in a 1. Negative 1, thank you. This is a 1 equals, if I plug in a negative 1, this ends up being 5a. What happens to this one right here if I plug in a negative 1? That turns into a 0. That whole thing is gone. So what do I know A is? A is 1/5. Now, it is ugly. Okay, everybody listen. Okay, at this point right here, you have a couple of different options. If you wanted to plug in A equals 1/5 here and then distribute it through and collect all the like terms and all that sort of stuff, that would be totally okay. All right? Usually, if you have a fraction, it's usually not a good idea to use this just yet. So we're going to hang on to this. We're going to keep this in our back pocket, and we're going to write down the system of equations. So we're going to distribute through here, and here's what we get. So this side is a 1, and then I get, let me change colors here. We're getting there. Okay, let me distribute through. So this is going to be ax squared plus 4a. This one's going to be plus bx squared plus bx plus cx plus c. Everybody okay with that? Okay, now over on this side, I'm going to collect the squared terms together. So again, start a set of parentheses. I've got an a and I've got a plus b. and those are both x squared. So I'm going to cross those off. Any questions there? Next, do I have any x terms? Right here and here. So start a set of parentheses, put a plus, start a set of parentheses. I've got a b and I've got a c, slap the x on the end. And then I've got a 4a and I've got a c. So that's going to be start a set of parentheses, 4a, and then I've got a c. Now that I know how many terms I have over here, you don't have to write this, but I kind of like the symmetry. I have no x squareds over there. I have no x's over here, but I do have a 1. And then I'm going to go through and I'm going to color code these. Yeah. But they make up the plain old number on this side. That's a plain old number and that's a plain old number. So if I put them together, they have to be the plain old number. Okay. Anything else? Okay, watch. Question? We're going to get there in just a second. We're almost there. You probably wouldn't want to do it right here. Okay? So what I'm going to do is I'm going to look through here and I'm going to say, hey, you know what? Whoops. Put that in the right place. A plus B had better equal 0. A plus B had better equal 0 because that's the squared term. If I look here, B plus C had better equal 0. Okay? So 0 had better equal B plus C. And then if I look at this last one, I'll highlight that. 4a plus c had better equal 1, right? So for that last one, 1 had better equal 4a plus c. Now at this point, okay, notice I've only had to work with fractions once and it was like writing down the answer. I've gone through here, haven't had to deal with fractions at all, but take a look at how cool this is. A plus b had better equal 0. What that means is a equals negative b or vice versa. Thank you. Okay? Or if I write it like that. So what does b have to be? If we know a is 1/5, b's got to be negative 1/5. Got that one. Okay? Let's take a look at another one over here. If I know what a is, so if I knew a was 1/5, this is 4/5 plus c. If I move that 4/5 to the other side, that would be minus 4/5. So that means c is going to be equal to 1/5. Yeah, you could do that also. Okay. Again, so what Parker's pointing to is a lot of times you won't need all three of these. You can use that last one just to double check and make sure that you got it right. This one says that b plus c had better equal 0, and this is negative 1/5. I found that this is 1/5. Negative 1/5 plus 1/5 is 0. Pretty good confirmation that we got it right. So let's come back up here. Let's see. A and c are positive, and b is negative. So let's come back up here and let's write the answer. So the answer is a is 1/5, so I'm going to write 1/5 over x plus 1. Then I'm going to write plus negative 1/5 x plus 1/5 over x squared plus 4. Is this okay to write the answer that way? It's okay. Is it the best way? It's not, and we'll fix it in just a second. Tylin. Right. Just the 1/5. When you factor it out, you just factor out the 1/5. Okay? So this is going to be 1 over 5 x plus 1. Okay, now I'm going to take out a negative if that's okay. So I'm going to write minus, and then I'm going to have a 5 here and an x squared plus 4. And then the numerator is just going to be, took out the negative, it's going to be x minus 1. Okay, now that's a lot cleaner looking. I mean, that's a nasty problem. Okay, but not too bad. I'll accept this. This would be great if you could do that. Any questions? Okay, are these as bad as they seemed? Okay, everybody but Tylin can answer that question. Are these as bad as they seem? Hopefully not. Okay, let's take a look at this one here. Again, the nice thing about this, factored, not so nice. Okay, has a repeating linear factor. Go ahead and break it into its parts. Give you about 30 seconds to do that. This should be a very quick process, especially when it's already factored. Definitely need one for the x plus 2. Definitely need one for the x plus 1 quantity squared. There had to be one with a quantity squared there. There could have been one with just a plain old x plus 1. Okay, this is that whole idea. I've said this phrase a couple of times. We want to break, each factor gets its parts. Okay, so one for each one of the factors and its repeats. One for this one right there. One for this one right there. And its repeat. Okay, so there we go right there. So a factor of x plus 1 and then its repeat factor over here. Questions? All of the factors are degree 1. All the numerators have to be degree 0. So that means I've got an A, a B, and a C. If I multiply by the denominators, x plus 3, A, x minus, thank you. Okay. And this would be x plus 1 quantity squared. This one's going to be B. X plus 2 gets to stick around and only one of the x plus 1s cancel. And then this is going to be C. And what does it get multiplied by? C and x plus 2. Any questions? Any convenient zeros? -2. Okay. Okay. So let's plug -2 in first. -5. See, -2 plus 1, that's -1 squared. That's just going to be an A. What happens here and here? They have a factor of x plus 2. When you plug in a -2, both of those go away. So we have one of our answers right there. Other convenient zero? -1. So we're going to plug in a -1. That's going to give us -4 here. That's going to go away. That's going to go away. And only the one with a plain old x plus 2 gets to stick around. We're plugging in a -1. So that's a -1 plus 1. That's a 1. So I get a C. So look how easily those drop out. There are the answers. Okay, once you run out of convenient zeros, okay, usually a system of equations is a good idea. Are you pretty comfortable with system of equations? You should be. Okay. Okay, let me, I'll tell you what, let's see if we can, I think we might have time to do this. There's one other thing that you can do. There's nothing special about these other than that they're so convenient they make a bunch of stuff disappear. Okay? What if I just said, hey, you know what? What would happen if I plugged in a 0? This side would be -3. This would be, it'd be a 1. So that's an A. 2 here. 1 here. Times them together, that's a 2. Okay? So that's 2B. And what's this one? 2C. Take a good look there. Okay, now, that's not a convenient 0, but it is a fairly easy number to plug in, isn't it? Okay, and look what we get. I've produced another true equation. How many variables does it have? Okay, it has 3 variables. How many do we already know? We already know 2 of them, so you could take those and you could plug them in. So -3 equals -5 plus 2b, and this would be -8, is that right? So if I move this stuff over, this is going to be, we're going to be adding 13. So So if I add 13, this is going to be 10 to b. So that means b equals 5. Oops, I'll do dotted. Well, it's not very stupid because sometimes you're stuck with that. Okay, this is just so if you thought of it this way, the only reason this works is because we already have 2 of these answers. If we only had 1 of these answers, we'd have to produce 2 of these equations like this. Then you've made yourself a system of equations anyway. There's no way to get around knowing how to do systems of equations. Okay?
But if we do have to, we can just do this.
If there were a problem just like this on the test, assuming you could remember how to do it, yes, you could. Okay? Any questions? Okay. Just for the heck of it, this side turns out to be x minus 3. I'll change colors so we can keep these straight. This side turns out to be x minus 3. This is x squared plus 2x plus 1. This is x squared plus 3x plus 2. So if I distribute through, I get ax squared plus 2ax plus 2, or sorry, plus a. This one's going to be bx squared plus 3bx plus 2b. And this one's going to be cx plus 2c. If you go through and solve that using a systems of equations, you will find that b equals 5. Okay? I haven't seen one. I've done these for a long time, and I've never seen one where that middle one wasn't a number. Okay. Although we could make one, we could take the starter question and work backward. Okay. Question? Sure. Mm-hmm. Yep. You wouldn't, okay, so you want to use convenient zeros because those are going to produce answers immediately. Okay, so on this one, there were 3 undetermined coefficients. We found 2 of them very quickly, and then if you just want to pick a number and make an equation that you can plug the other 2 into, it will work very quickly. What if we had 3 undetermined coefficients, but only 1 convenient zero? Then you're going to be stuck using a system of equations either way. If you wanted to get this one and then plug in a 1, make an equation with a, b, and c. Plug in a 0, make an equation with a, b, and c, and then solve that by plugging in whatever a was or whichever one we happen to have. Okay, you could do that. Okay, I find so there are lots of different ways and kind of ways you can mix these techniques together. What you should do is you should practice doing it. So the way I've shown you up until this point right here, I'm not a huge fan of this just because people forget how to do it and why it works the way it does. Okay, and they think, oh, he just plugged in a 0. I'm going to plug in a 0 and the answer is going to drop out. It doesn't work that way. Okay? All right, so let's take a look at the last one. Oh my gosh. Yeah. You do. Yeah, you do. So I'm trusting that you can do that at this point. Okay? John's going to make me be honest. So let's see. We've got a negative 5, x plus 2, 5 over x plus 1, and then c is a negative 4, x plus 1 quantity squared. If you wanted to slide that negative out front, you could do that. Okay? Questions? Okay. All right, let's take a look at this last one. At the risk of going down completely the wrong road, Tylin, what's the problem with this one? In what way? In what way? It doesn't factor, okay? Okay, this is an irreducible quadratic. I mean, it's already factored as much as it will go. We've got x squared plus 4 quantity squared. So there's nothing else we can do factoring-wise, but let me say this again for probably the 6th time. We're going to make a part for each factor and its repeats in the denominator. So what's the first one we write down? X squared plus 4. What's the next one we're going to write down? It's repeat, so we're going to write that, and we have quantity squared. Now this looks absolutely awful, doesn't it? Okay, it actually works out to be pretty nice, so don't give up on this. This is actually cool that it is this complicated, and the answer works out to be pretty nice. So the factor is degree 2. The numerator is going to be an ax plus a b. Again, we're saving places for all the possibilities. The factor is degree 2. The numerator is going to be degree 1. So that's a cx plus a d. Next, multiply it by x squared plus 4 quantity squared, because that will cancel off the denominator, and look what we've got. We've got x cubed plus x squared, just like it always does. Okay, it's just the numerator there. And then this is going to be ax plus b times x squared plus 4. Because we're multiplying by 2 of them, only one of them cancels. What's the next one? Cx plus d. That's not so bad, is it? Now, how many undetermined coefficients do we have? We have 4. Do we have any convenient zeros? None. We don't have any convenient zeros. Okay? So we are stuck using a system of equations of some sort. Okay? So let's do this. This side is, if I distribute through, this side is ax cubed plus 4ax, then bx squared, then 4b, then cx, and then d. Okay, watch. Again, we're going to collect these together. Thanks. We're going to collect these together. There's an ax cubed. There's only one of them. Let's look for squares. There's only one of them. This should be looking pretty promising at this point. Let's look at the x terms. Thank you. 4a, c, and an x, right? Nope. We've got a 4b there and a d. Those are the plain old numbers, so 4b plus a d. On the other side, I'm going to write 1x cubed. Make sure I write squared this time. 1x squared. No x's and no plain old numbers. And then we go through and you can look at this and you can solve it. There's only one x squared term here, and it's got an a in front of it, and it better equal 1x, cubed. Ax cubed and 1x cubed. What's a? A is 1. Got that one taken care of. There's only one x squared term and one here, so b has to equal 1. 0x has to equal 4a plus c, so that's got to be 0. And then 4b plus d has to equal 0. So this is, let's see, if I plug in what a is, or if I just said c equals negative 4 times a, c is going to be negative 4. And if I move that over to the other side, d equals negative 4b, so that means d equals negative 4. So even the system of equations on this one was pretty easy to solve. So now we're going to come back up here and John's going to tell us what to write. What's the answer? Because they're both negative, that's good thinking. Let's pull the negative out front. I'll write the denominator. And what do I write up here? 4x plus 4. Okay? And there it is right there. Okay? Any questions? Okay. You will have a quiz tomorrow. It will be no more difficult than anything that we've covered on the lecture notes. So if you know how to do the lecture notes and you're done with 8.5 when you walk in tomorrow, you can just start working on the review, ask questions and stuff like that. Make sure you're in great shape for the test on Tuesday.